All right. Hello, hello. Happy Sunday. Welcome. We are looking at Unit 2 today. Um, as you're just coming in, drop a hello in the chat to let me know you're there. And also grab some paper. We are going to be doing some practice problems today, so you might need some scratch paper. Great. So we'll get started in about a minute, just giving people time to jump on. If you're just coming in, hello, welcome, happy Sunday. Oh, Kristen is here in the house, ready to go. Hello, hello, welcome. Like I said, we'll give everyone just another minute or so to jump on and then get started. If you want to play along today, we are going to do some practice problems as we dive into Unit 2. So grab some scratch paper. We'll get started in about 30 seconds. I'm excited. This is a monster of a unit, but it's a good one. So I'm excited to dive into it with you all today. Just another couple moments. If you're just coming in, hello, grab some scratch paper. We'll get started in a second, and we're going to do some practice problems as we work today. So will be helpful to have some paper, maybe even a calculator. Things are going to get real. So let's get going. We are going to dive into Unit 2 today, which is Newton's laws. So let me share my screen and we will get going. Here we go. Great. So a couple things as we get started here. First one, just a reminder that we are recording this. And so if you use your name, or if you ask a question, I might call out your name or your name might appear. So just if you don't want your real name anywhere, change it. And just always a plug here to follow Fiveable on all of the social media, so Twitter, Instagram, YouTube. We are here to help as you are starting to really gear up for APs. So go ahead and if you haven't yet given us a follow, please do. Today, like I said at the beginning, jumping in, big unit, lots to do. So first thing we'll talk about is just we're gonna run through all three laws of motion. We'll talk about static and dynamic equilibrium, and do an example problem. We'll then really dive into what happens when there's friction. So friction complicates things, so we'll talk about what goes on there. And then we've got a couple of special cases here. We're going to talk about pulleys and Atwood's machines, and then we're going to talk about what happens when we've got a ramp. So that's the roadmap for this stream. And we're just going to go because, like I said, lots to do today. So first here, Newton's laws of motion. So first key idea, we'll talk about the first and the second law. We'll talk about static and dynamic equilibrium, and then briefly touch on Newton's third law. So first and second law, really, this is just the second law because Newton's first law is just a special case of Newton's second law. So first, let's just talk about what it is and how it works. Newton's second law says that the acceleration of an object is directly proportional to the net force or the sum of forces. You'll hear me say both. Those are the same thing. And inversely proportional to the mass. So that's like a lot of words and they're kind of big. The easiest way to think about it is if we take the net force or the sum of forces on a system, it's going to be equal to the mass of the system times the acceleration. So F equals ma. At the bottom here, you can see what it looks like. I just scrolled over the thing, but it will go away in a second. There it is, what it looks like on your equation sheet. It's written as an acceleration equals expression. Those are all the same thing, just written in different ways. So it looks really simple, but we're going to talk about this law for like pretty much the whole time. So there's a lot to do with it. And just in the box here, just a side note, Newton's first law, all it is a special case of Newton's second law. It just says that if that sum of forces is 0, then there's no acceleration. So either if the object is at rest, it's going to stay at rest. If it's moving at a constant velocity, it's going to stay moving at a constant velocity. But that makes sense if you look at the equation, right? If the F is 0, then the A also has to be 0. So that's like pretty chill, and we don't really have to worry too much about it. Great. So we need to talk about equilibrium. So first, what is it? Equilibrium happens when the net force on an object is 0. So when we've got that sum of forces is equal to 0, we're in equilibrium. And then by definition, we know from Newton's second law that when that happens, the object is not accelerating. This is going to be a really powerful idea, and we'll do some examples with it, but really it's going to be really powerful because a lot of times the object isn't accelerating in at least one direction. And so we can kind of put that 0 in and do a lot of math, and it makes it, it makes that math kind of open up to give us more ways to solve for the forces and things that we need. So this is a powerful idea that we're going to apply a lot today. Quick note, there is a difference between static and dynamic equilibrium. Static equilibrium is exactly what it sounds like. Object is at rest, it's static. Chandelier hanging from a ceiling would be an example of static equilibrium because the chandelier isn't moving at a velocity, it's just at rest. We can also have something that's in dynamic equilibrium. That's when the object is moving at a constant velocity. So net force is still 0, it's not accelerating, but it is moving. So that's kind of a weird one to sometimes, you got to just kind of like think about that one for a second, right? Because you're like, oh, it's moving. Shouldn't there be forces on it? But not necessarily. If it's moving at a constant velocity, that means that even if there are forces on it, those forces are kind of canceling each other out. We see that word equal in equilibrium, right? They equal each other out, and the object is not accelerating. So we're going to do an example. This first example I thought I would walk you through. We are going to do some practice questions and some poll questions and stuff throughout, but really the setup for these is going to be, some of the steps are going to be pretty similar every time. So the first one we're going to do together so I can show you the steps, and then you can practice them a bunch of times later in the stream. So here's our first one. We've got a 2 kilogram sign, hangs from the awning of Joe's Pizza. Joe's Pizza is not a real place. I made it up, but it will work for this. We're looking for the tension in each of the ropes that hold up the sign. So my first thought always when I look at something like this, I'm like, oh man, there's like almost no info here, right? All I know is the mass of the sign, and I know the angles of the ropes. We see 45 and 60 up here. But that's actually enough to answer this question. So there's going to be some steps to go through anytime we start looking at these force questions. Tension, remember, is just a special name for what's the force in each of the ropes. Ropes have tension. It's a specific kind of force. So we're looking for the force in each of the ropes. So there's a lot of words here, and we're going to walk through it together. Notice first that I color-coded for you, and I purposely put all this on here so that way when you look back at this stream and back at these slides, you've got like a full-on example, because most of this actually is just math, and it's algebra. It's not even calculus, but that doesn't mean that it's easy, right? So the steps are in black. I've got a couple notes in different colors throughout, and then all of my work, like if I were to be writing this on the test, is going to be in blue. So first thing we're always going to do is we're going to draw something called a free body diagram. All that is kind of a diagram that's showing those force vectors pointing in whatever direction that they are acting. You're always going to have those arrows pointing out from the center of the object. That's actually like a rule, so you have to do it that way if you get asked to draw one of these, a free body diagram. And then you can see that, so I guess how I did it, if we just talk through it, we know that gravity is acting on the sign. It's pointing down here. And then each of the ropes is holding up the sign. So we've got T1 pointing in this direction, T2 pointing in this direction. Now, I did want to just briefly talk about geometry. It's not my favorite subject, but it is useful here. You notice that I put this 45-degree angle right over on this left triangle here and the 60-degree one here. That's because of geometry. So if we go backwards just a second, we see that this is a 45-degree angle. There's a geometry theorem. I forget what it's called, but it's something like vertically opposite angles are equal. So basically, if you've got something in this corner, it's going to be equal in this corner. If you don't remember it, we do remember that a straight line is 180. So you could kind of work your way backwards to get to this 45-degree angle here. So I drew my forces out. I've got them labeled. And then in green, I drew my components. So hopefully you're at the last stream. In the last stream, we talked about how to get the components of a vector. If you haven't, definitely go look at it. But basically, I just drew triangles here to tell us about what the part of the force acting in the x direction and the part of the force acting in the y direction is for each of these angled forces. Great. So we did that for both of those angled tension forces. And now we've got enough info to write our net force expressions. So the way we're going to do it is we want to separate the x and the y. X and y are always independent no matter what you're doing. Could be, in the last stream we talked about projectile motion. Here we're talking about forces. General rule of thumb, keep them separate. Combine them just at the very end. So I wrote my net force expression in the x direction first. So I've got this positive T2 cosine 60 of this, the T2 force, and then this T1 cosine 45 is pointing in the negative direction. So you're going to subtract it. And then in the y, we've got 3 because we've got the y components of each of the tension forces pointing up, and then minus the force of gravity pointing down. So those are my net force expressions. You're going to want to do that pretty much every time you tackle one of these force problems. And then now we have to think about what's going on with that net force. Is it in equilibrium or not? If it's in equilibrium, which again is either at rest or moving with a constant velocity, then we know that our net force is going to be 0. If it's not, we'll talk about that later. We're going to plug in something else. But for now, we're plugging it in 0 because we know the sign isn't moving. And from here, you just do a whole bunch of math. So we're looking for T1 and T2. We run into a problem because there's T1 and T2 in both of those expressions. But we also are super great math students and know that if we've got 2 equations with 2 variables, we can use a system of equations. Small note, for the FG, I plugged in mg. That's the definition of the force of gravity. It's weight, right? And it's equal to the mass of the object times little g, or 9.8 meters per second squared. So that's where that came from. And then here, I'm not going to go through all the math that I did. You are free to look at it. The short version is I solved one of the expressions for T2, plugged it into the other one, got an answer for, just like plug a bunch of stuff into my calculator basically, and got an answer for T1, and then took that answer, plugged it in to get an answer for T2. Awesome. So at any point, I'm gonna pause here. At any point, stick questions in the chat. Kristen is definitely here to help. She's my chat guru, but I'll also be checking kind of as we go. So I don't see anything right now, so I'm gonna keep going. But if you have questions as we go, definitely stick them in the chat and we can pause. Okay, so that is kind of a general how we solve for forces and specifically what happens if it's in equilibrium. We're going to talk about Newton's third law for a hot second. This is like, you're going to maybe see a multiple choice question on it, but this is like not a huge deal usually. Newton's third law says that forces are equal and opposite. So if we think about it, when you exert a force on something, it also exerts a force on you. That force, the number of it is equal. So the magnitude, that's the number, right? That's equal, but it's pointing in the opposite direction. The name we give to this idea is an action-reaction pair. So if you're specifically asked about action-reaction pairs, this is what it's asking you about. And you can see the example here. Again, Kristen's awesome and always tells me to put more pictures in. So this is a great picture. As the arms, we don't know, it's just arms. As the arms are pushing on the wall pushes back on the arms. Those two vectors are equal in magnitude, so they're the same amount, but they're opposite in directions, so they're pointing in different directions. So we're going to do a quick practice problem with this. Here we go. So here is a multiple choice question, and I am going to open a poll for you all so that way we can practice. So we've got a motorboat speeding through a lake when suddenly a bug flies into the windshield and goes splat. Which statement's true about the forces involved in this interaction? So this is like, if there is like one Newton's third law question, this is it. It's always like this. So like this is like my default question for this always. I am going to open up a poll and let's see if we can't just quickly throw some answers in. What do you think? I'll stop talking. Take another 20 seconds or so. All right, last chance. If you want to take a, even if it's a guess, just throw something in there. Okay, great. So let me show you what we got. So the correct response here was C, and let's talk about it. To those folks that put A, I'm so happy you did, because this is can be such a trick question, and I'm happy that we get to talk about it. So thank you for doing that. When we look at these answers, because we said A and C, I'm going to focus on those two. C is the correct answer. Newton's third law, as a rule, tells us that the force of the bug that hits the windshield is going to be the same as the force of the windshield on the bug. That's an action-reaction pair. Those forces are going to be equal and opposite. However, that is like so not what you logically think the answer is, right? Because you're like, the bug is so much smaller, so it's going to exert a smaller force. It's not the force that's different. The thing that's different between them is the acceleration. So the bug has a smaller mass, so it's going to have a much bigger acceleration. That's why it goes splat, right? But the actual force that happens between those two objects is, by rule, by Newton's third law, because he said so, always going to be the same. So anytime you see a question like this, that answer is always going to be they're equal and opposite because of Newton's third law. If you have questions about that, please, please, please put them in the chat. Cool. Okay. Oh yeah, there, I just said that. Cool. Okay, so let's talk about friction. So friction here, two things to talk about. The first one is specifically static and kinetic friction, what they are, how they work. And then we're going to briefly touch on drag force, and I'll tell you why briefly when we get there. So, a lot to do with friction. First thing, what is it? It's the interaction between objects and its surroundings. So I also teach chemistry, and so I always like to just I go on this weird chemistry tangent about this, but basically the atoms in the things, in the objects, have electrostatic forces, and those interact, and that's why we have friction. That's the fastest I've ever explained that. There are two types of friction. The first one is static friction. Static friction happens, I put it in red because the object is not moving when it's got static friction. It's at rest. Kinetic friction is in green because the object is going to be moving when we have kinetic friction. Also important to note that objects, like if you've got something that starts at rest and then you push it and then it starts moving, it's going to start with static friction and then it's going to change to kinetic friction. And those two types of friction are not always going to be the same. Friction depends on two things. The first one is something called the coefficient of friction. We symbolize it with that funny looking U thing. It's mu. It's a Greek letter, mu, mu. And what it is basically is a constant, and throughout a surface, it's going to have the same mu, and it tells us how slippery it is. So bigger mu values are more friction filled. So like sandpaper has a much bigger mu than ice does. All of those numbers are going to be less than 1 though. So by bigger, I don't mean like the number is really big, but big relative, right? So sandpaper is going to have a number much closer to 1 than ice would. And then the other thing it depends on is something called the normal force, symbolized with an F sub n typically. And that's a force that's specifically exerted by surfaces. And if we think about it, a lot of you right now are probably either sitting or standing. So you're experiencing normal force right now. I'm sitting at my desk, and the chair that I'm sitting on is exerting normal force up at me, so that way I don't fall to the ground. And then if I were on the ground is exerting normal force up at me, so I wouldn't keep falling towards the center of the earth. So that's all normal force is. The way that we calculate friction, it's actually on your equation sheet. It looks really funky, so ignore, it's just telling you that you want the absolute value of the numbers. But basically, the force of friction is going to be less than or equal to the coefficient of friction times the normal force. So that less than or equal to is like kind of a funky thing. And really, it just depends on what type of friction you're looking at. So again, we're color coded. The red one here is static friction. Basically the reason that it's less than or equal to is because the static friction is going to keep increasing to a maximum. And then once you hit that maximum, the object starts to slip or to move. And then that friction turns into kinetic friction. So the less than or equal to is like, it is because the static friction can change based on how much you're trying to get it to move. And they're always going to be equal to the coefficient of static friction times the normal force. Kinetic friction, general formula is the same, but it's always going to be equal to, because the kinetic friction, once it's moving, isn't going to change. So we've got the force of friction is equal to the coefficient of kinetic friction, which is a different number than the static friction, and then the normal force. So I'm saying a lot of things, even as I'm saying it, I'm like, this is a lot, and it's kind of confusing. The short version here with these formulas is like, you've got your friction, you've got your coefficient of friction, and you've got your normal force. Almost always, you're going to put an equal sign in the middle there, because if you're talking about static friction, really you're looking to see if there's enough static friction to keep it still, or if there's not, then it will start moving, and then you've got kinetic friction. So get the gist of the formula, and then we'll just apply it. Okay, so here's an actual practice exam multiple choice question having to do with kinetic friction. I had to read it. Kinetic friction. So here we've got a block of mass M pulled across a rough surface. When we see that word rough, that's telling us that there's friction. It's like the problem being like, it's rough, it's not smooth, there's friction. We've got a diagram. Coefficient of friction between the block and the surface is mu sub k. The force F pulls the block, exerted at an angle phi, I believe is that Greek letter shown, which is an expression for the magnitude of the frictional force on the block if it's moving at a constant speed. So in a second, I'm going to open a poll. I'm going to give you a little bit of time to do this, because this one's going to take a couple steps. First thing you're going to do, and ignore me if you don't want spoilers, but the first thing you're going to do is draw a free body diagram here. And then the second thing you're going to do is write those net force expressions in X and in Y, and then see if you can get an answer for the friction. Remembering that you have that extra friction equation now. So I'm going to give you a second to try it. Let me open it up. And then I'm obviously going to go through the answer too. So if you can't get it, that's okay. But I'm going to give you a solid minute or two here to try it. And I'm going to, again, stop talking. take another 30 seconds. That might be ambitious, maybe another minute. All right, last chance. If you're gonna pick something, pick it now. All right, cool. So let's go over this one. I think people were probably still working. This was a big ask of me. There's a lot of steps here, but this is a multiple choice question. So if you didn't do it now, maybe come back to it and try it again after. But here we go. So first thing, draw that free body diagram. So as we look at this, we know that we've got the force of whatever the thing pulling it is here. We called it F in the problem. We've got friction, and friction is always going to act in the opposite direction of the motion. So if the force is pulling it kind of towards the right there, the friction is going to act towards the left. We've got the normal force pointing up because it's on a surface. And then we've got gravity. You pretty much always have gravity. As long as you're on Earth, you've got gravity acting on the box. From here, we write net force expressions in each direction. So in the x direction, we've got the x component of that force F, that pulling force, and we're going to subtract friction because it's going in the opposite direction. In the y direction, we've got the normal force pointing up. We've got F sine phi pointing up here because it's the y component of that angled force, and then gravity pointing down, so we're going to subtract it. Next step, equilibrium, or is it accelerating? So the problem tells us that the block is moving at a constant velocity. So if we got stuck, maybe this is where. This constant speed here cues us that we are in equilibrium, which means that the sum of forces in the x direction and the sum of forces in the y direction equals 0. So anytime we see anything telling us about, the velocity or the acceleration or anything like that, that's helping us to know what to do at this step to help us to kind of move forward. So we know that we are 0, so we can plug in. And if I look at my answers here, I know that I'm looking for an expression for the friction. And I see in my work that the friction only happens, there's only frictional force, listed in that sum of forces in the x direction. So I'm going to focus on that one first and see if it gives me an answer. And because we're looking at the answer, we know it does. So we plug in 0 for the sum of forces in the x direction because we know it's moving at a constant velocity. And then we've got that's equal to the F cosine phi minus the frictional force. And then all I did is just, moved that frictional force over, and we know that it's equal to F cosine of the angle. So that answer is B. If you were looking for something else, like if it was asking for, the normal force or something like that, you could also plug in that 0 for the y direction and continue to find expressions for other forces. So that's kind of a general what we do with friction here. Let's talk about drag force. So the next one here, drag force, what it is when objects are moving through some sort of a fluid. So air, water, things like that. And that fluid is exerting a resistive force on the object. So it's noted with an R or an FD, and it always acts opposite the direction of the motion. There's two possible formulas for it. Pretty much always you're going to see this first one, but I wanted to just show you that there is a second one in case you happen to see that on the test. You don't freak out about it. It's a second one. It's more complicated, but most of them are constants. So they'll have to give you a lot of these numbers for this second formula if it is what they want you to do. But most of the time you're going to see it as this first formula. And really, we're not going to do a full example here because pretty much once you know that this is, how it works, and talking a little bit about in the next slide about terminal velocity, then all of the things we've been talking about apply to drag force as well. Sometimes you have to do something called separation of variables with it, which is a calculus thing. But again, this is like not, we only have an hour, and this very specific example, drag force, is probably not worth your time because a lot of the, so much of the test is just on kind of like regular forces with no air resistance. Then that I just wanted to kind of show it to you, talk about terminal velocity for a moment, and then really focus on the other stuff. So terminal velocity is a special name we give to the max velocity of an object that is falling when it says when it's reached dynamic equilibrium, which just means that the force of gravity acting on the object is equal and opposite to the drag force. So if we look at it in terms of a graph, that velocity is going to be increasing because the acceleration due to gravity is going to be 9.8. So it's going to, that force of gravity is going to pull on it. It's going to get faster. And then at some point, that force of gravity will balance out with the drag force. And when that happens, the object stops accelerating, reaches its terminal velocity, and then that velocity becomes constant. And it looks like this on a free body diagram. Cool. Special cases. So I wanted to spend a good amount of time today working on special cases. And I want to give you some practice with it because you're going to see these like almost definitely on the test. So I wanted to really kind of do more force practice, but in the context of these special cases, because they're going to be important. So first one here, it's called an Atwood's machine. And more generally, we're talking about pulleys. So for now, when we're talking about this, these pulleys are going to be massless, so they're not going to have any mass, and they're going to be frictionless. So there's no effective friction as the string is kind of moving along on the pulley. That will change later as we get, through the units. Once we start talking about things that are rotating, that no longer necessarily applies. But for now, massless, frictionless, and the tension is going to be the same throughout all of the string. So there's some tips here. First one is to adopt a sign convention. So thinking about which direction do you want to be positive. And then the second one is we're going to use Newton's second law with this, right? So our steps are going to be the same for these as they were for the other problems. So first thing we'll do is draw a free body diagram of each of the blocks here. Then you're going to write your net force equations. And what I mean by adopt a sign convention is instead of thinking about positive as up and negative as down, what we can do is we can say, okay, if the block is moving in this, or if the blocks are moving in this direction, then this direction is going to be positive. So in the direction that the blocks are moving, we're going to make that positive. And then in the opposite direction, we're going to make it negative. Again, I'm going to show you an example in a minute. So when we do that, we can simplify our thinking because we're not as worried about like moving up, moving down. We're moving either with the acceleration or against the acceleration. So here's an example. I'm going to give you a good amount of time to work on this one because we have to go through the steps again. So we've got two masses. They're hung at rest. And it says, again, massless cord, massless frictionless pulley. That means just don't worry about it. If the first mass is 5 kilograms and the second mass is 8 kilograms, once it's released, we want to find the resulting acceleration of m1. So we're going to work on this one. I'm going to give you a second to get started. I'm going to interject in case you get stuck, just with some tips, so that way I can definitely get you going. But I want to see if you can get started first. If you have questions, always put them in the chat. We are here to help, and then we will look at the answer. So just to interject in case you're, stuck right now, first thing we want to do is write those net force equations, right? So think about how, or the free body diagram. So think about how each of those masses has gravity acting on them, and then tension from the string. And then once we've done that, we can either write one net force equation, including both blocks, or separate ones. And then we should go from there. Take another minute, and then we'll look at the answer. All right, if you're going to answer right now, now's your time. Okay. So here we go. Let me show you what we got. So half of us got it, and half of us, I know what you did wrong, and I wanna show you. So I was smart about my wrong answers this time, so I want to show you what happened. So let's talk through it, just all the way through, just in case. So first thing here is to draw a picture and to decide which direction is positive. So I drew out my pulley, and I decided that because I knew that the N2 was going to be the bigger force because it's a bigger mass, I decided that it was going to go in that direction, right? So I decided that moving in that direction was going to be positive. So that's the first thing. Then I drew free body diagrams for each of the masses. So they both actually look identical. I color coded so you can see my 5 kilogram mass 1 is going to be in yellow. My 8 kilogram mass 2 is going to be in green. Both of them have gravity acting on them, so the force of gravity or force of weight will go down. And then both of them are connected to that rope, so the tension force goes up. From here, I'm going to write sum of forces expressions. And I'm going to write them for each block first. And then, well, I guess here, let's do it this way. So there's two ways to do it. You can either write sum of force expressions for each block. If that's how you did it, that's great. Both of them will look the same. You would have the sum of forces is equal to the tension force minus the weight for the green block. And then for the, no, yeah, that's true for all of them. Tension force minus the weight. For me, having then two net force expressions is like more complicated than actually just combining them. So another trick you can do for these Atwood's machines is combine the masses and treat tension as an internal force. What I mean by that is because the tension itself isn't actually causing the acceleration and it's acting on both of the masses, we can just keep it kind of internal and pretend like it's not even there. And if we do that, then the only external forces acting on the Atwood's machine, on the masses, are the two weights. Because we know that the weight of the 8 kilogram block is going to be bigger than the weight of the 5, and we know it's going to go in this positive direction that I identified, then we know that the FW of the 8 kilogram minus the FW of the 5 kilogram block is going to be equal to the sum of forces. From here, all I have to do is plug in that weight equals mass times the acceleration due to gravity to get an expression for the sum of forces. So if I look at this, all I did is plug in the mass of the green one, which is 8, and the mass of the yellow one, which is 5, and I see that my sum of forces is equal to 3 times the acceleration due to gravity, which if you wanted to calculate that out, you totally could. So now here, I want to show you, because this is going to be now the first one that's not in equilibrium. It's actually moving. It's accelerating, right? So the way that we handle that is instead of putting a 0 for the sum of forces, what we would do is we would plug in Newton's second law. So we would put in MA for the sum of forces part. So we've got the sum of forces, we have it equal to 3g up here, and we're going to have it equal to MA. So we get that far, and then this M, this is where it's tricky. And I think likely for those of you that put the 3.6 meters per second squared, this is where you messed up. So the way that we treat this, if we are treating it as one big system with only the weights on the outside, then the mass of the system is actually both of those masses added together. So we've got the 8 kilogram block and the 5 kilogram block. Those are kind of like now smushed together as part of the system, and the only forces acting outside of it are the weights. So because they're both smushed together as part of the system, you have to add their masses. So we've got 8 plus 5, which is 13. And then I need to stop doing that because this thing keeps coming up. And then all we need to do is plug in and solve for A to get 2.26 meters per second squared. I'm going to check the chat and make sure we don't have any questions. Oh, yeah, nice. Thanks, Kristen. Great. Okay, cool. So we've got one last special case to talk about, and then, let me get rid of this poll. One last special case to talk about, and then we'll just answer any questions that you have lingering. So for this one, this is probably the most complicated special case, but I did want to talk about it because you are probably going to see it. And there's a couple tricks to help us when we look at ramps. So if an object is on a ramp, the reason that this is a little bit more complicated is because in like regular situations, when the object is not on a ramp, then the normal force is going to be equal and opposite to gravity. In this case, that's not true because the ramp is at an angle, right? So in this case, gravity still points down, but the normal force is going to point at that angle, which is going to be normal is like perpendicular, fancy, right? So it's going to be perpendicular to the surface of the ramp. So the normal force will point along what I've labeled as the y-axis here when we're looking at ramps. And the easiest way to deal with ramps is we do something called the head tilt. So I don't know if anyone watches Schitt's Creek, but I love it. So Alexis is modeling the head tilt for you because you can't actually see me. All we need to do is change up our axes. Instead of being like the normal vertical and horizontal axis, we're going to make the x-axis go along the hypotenuse of the ramp triangle here. So it's going to be parallel to the surface of the ramp, and the y-axis is going to be perpendicular to that. If we do that, then most of your forces acting in this situation are going to be on one of the two axes. The only one probably that won't be is gravity, and we can do again some like special geometry. And I'll just tell you, and you should just remember that in these situations, the angle of the ramp is going to be equal to this angle between the y-axis and the force of gravity. So those two angles are going to be the same. Again, it has to do with some fancy geometry, but you could just remember that. That's going to be a shortcut. So if we do that, then when we set up our problems, most of the forces are going to be on one of the axes, and we can treat it pretty much like normal. The only thing we'll have to deal with is getting this force of gravity into components, so that way we can write our net force equations. Okay, so this is a big question. There's a lot of steps here to get to coefficient of friction, so we are definitely going to unpack this one together. I wanted to kind of just stepwise our way through it. So even though eventually it's going to ask us for coefficient of kinetic friction, if you want to get there, great. But the poll question is going to actually be earlier than that. So the poll question here is just going to ask you first to write the net force equations in each direction. So I'm going to open it up so you can see it. I've got written in here f of x equals and then f of y equals. So right now, see if you can get to a point where you can draw a free body diagram and then write those net force equations. Don't forget to do the head tilt. And then from there, we'll see if we can get answers. And then if you want to keep going, keep going. If you want to pause there and just have me walk through the rest of it, we can do that part together. So that is up to you. I, again, will stop talking and give you a couple minutes to see if you can at least get to the net force equations in each direction, and then we'll go from there. Take another 30 seconds or so. And if you're going to answer, this is your last chance. All right. Great. So we are half and half again. So let's talk about it. So let me get rid of that. There you go. Okay, so we're going to talk about just the first part first. So first thing here is to do your head tilt, right? Do your Lexus head tilt. This time it's in the other direction because the ramp is in the other direction, but same idea. Draw your axes along the ramp and then perpendicular, and then draw the free body diagram. So if we draw this, we see that the force of gravity is not on an axis, but the other forces happening in the problem are the normal force coming from the surface and then friction acting against the motion. And those are the only forces in this problem. We know that we can break that force of gravity into components. And if we look at this, we have, oh, I have a mistake in here. We have this FG, this should be cosine of theta, and then FG sine of theta. I'm going to update this and make sure we get the right slides posted. But if we look at this, that should be flip-flopped. And so actually, the person who got it wrong, I think, is right, because I think I flip-flopped them in the answer. So this should be flip-flopped. So this should be FG cosine theta because it's adjacent. This should be FG sine theta. And then so when we write these net force expressions, we should get f of x equals force of friction minus Fg, this should be sine theta. And then this is the normal force minus Fg cosine theta. From here, we can answer the question. So we're going to use the sum of forces equals ma here, and then plug in here. So we know that the sum of forces in the x direction is equal to ma, and it's equal to the force of friction minus Fg sine theta. And then we're going to flip-flop this, right? So the sum of forces in the y direction is going to be 0 because in the y direction, the object isn't accelerating, right? It's not like floating into the air or going through the surface. So it's going to be equal to 0. And this is going to be equal to normal force minus Fg cosine theta. And then from here, what we're going to do is we're just going to use what we know about each force to solve. So this is like a lot of, this part is always like a little funky, and it's just a lot of kind of playing around with the different equations that we know. So we've got our net force equations. We also know that the force of friction is going to be equal to mu times the normal force. And so I'll walk you through what I did. This number is going to be wrong because my sine cosine is wrong, but I'll walk you through what I did, and then kind of just like generally remember that we kind of just need to plug in the different equations that we have for forces until we can kind of massage out what we're looking for. So here we go. We know that in the x direction, the mass times the acceleration is going to be equal to friction minus the component of gravity. We also know that friction is going to be equal to the coefficient of kinetic friction times the normal force. So what I did is I plugged in mu times the normal force for the force of friction here. Then from there, I also know that the normal force is equal to the y component of gravity because of this. So we know that this is equal to 0. So I can say that the normal force is equal to the y component of the gravity. So I plug that in here. Then again, we're kind of just still massaging. We know that the force of gravity is equal to the mass times the acceleration due to gravity. So I plugged that in for the force of gravity here. Luckily, we can start to simplify. We've got the mass is going to cancel because there's a mass in each term here. Simplify, and then all I did is plug in and solve for the coefficient of kinetic friction. So that's that. this is, again, definitely a more complicated problem, and you may not see all of the pieces of this problem. Like this was like beginning to end, how you do one of these. But the takeaways for these ramp problems are really to make sure that you do the head tilt and then to set up your axes. Oh yeah, Kristen is confirmed. Sorry, I'm just looking at the chat. Yes, you guys all corrected me. That's awesome. Sorry about that. That's also actually takeaway here. That's a really common mistake, and I just did it. But you should not do it on the test. So thank you for correcting me there. And like I said, I'll get the updated slides posted very soon. All we need to do is just flip sine and cosine in all of these expressions, and the rest of it I think is good. But yeah, thank you. So takeaways: do the head tilt, set your axes, and then get the correct components of your gravity. All right, wrapping up. When we're doing forces, keeping the x and y forces separate when writing net force expressions is always going to be important. X and y are separate for everything, but especially for this. When in doubt, draw a diagram, list what you know, what you're looking for, and really working to just kind of massage through the different force expressions to get to what you are, what you're asked for, right? So kind of bouncing between the frictional force expression and F equals ma, and making sure that you remember that the weight is equal to mg, and like all of those different pieces are important. And if you're stuck or struggling, you can always kind of just like plug in the different things and see if it helps you get closer to an answer. I would be remiss to not mention Star Wars at least once in the forces unit, because I feel like at this point I have to. So we've got Yoda there wishing that the force would be with you, I guess. And lastly, I always end with just take a deep breath. You can do it. These are going to be coming up a lot, so definitely look at forces, look at Newton's second law, and when in doubt, write those net force equations. Any questions? Oh yeah, okay, so let me look and see. Yes, so to answer the question in the chat, B is the correct answer. I just flip-flopped sine and cosine. So if you got B, you were right. Good work. Okay, cool. Any last questions? Stick them in the chat. Wrapping up. I'm going to stop sharing. Y'all can see how dark it got since I started. Great. If you have questions, you want to stick them in the chat, feel free. I also want to point you, let me share my screen one more time. I want to point you to Discord. Kristen will be in Discord right after this, so definitely go there. Our next cram is going to be next Sunday at 1, work, energy, and power. And there it is. So here's the link for the Discord if you want to go there next. Kristen will be there, happy to chat and answer any questions. And I think that's it. Thanks, y'all. Good to be with you. How do we practice multiple choice questions? I think in general, it would be it's actually really helpful to just Google like Unit 2, AP Physics C, Mechanics, multiple choice questions. Oh yeah, sorry, Kristen. Yeah. I didn't know you meant specifically these. In general, there's a ton of multiple choice forces questions online too. But yes, the slides will be here, and I will update them to make sure that last one gets fixed, so that way you have all of the correct answers. Great. Anything? If there's anything else, stick it in the chat. I can stick around for another couple minutes. Cool.